All right. Okay. So scroll down here. Since last class, I've realized in this class, my other one, I'm having some kind of an issue with my Kaltura videos on YouTube, and I'm not realizing they were flagged. So didn't record the class when I handed back the exam. That was just my user error. I forgot to start Zoom after I handed everything out. So, we've reviewed that material probably in the class before and the class after. So hopefully you were in class and got to see that anyways. But that class from last Tuesday is now up on the YouTube playlist. So it was for some reason flagged. I went through and kind of changed it and got the one uploaded from this Tuesday's class. So those are both up on YouTube now. I also added a set of sample questions to kind of prepare for that fourth quiz. So that was posted yesterday. I didn't post it until after I got those sample questions up there. So you can kind of take a look at those. Give you a good idea of the type of questions that I might ask you on that quiz. It'll really just be related to everything we've covered since the last exam, which is just this week 9-10 category, which was all this nonlinear relationship stuff. Now that fourth problem that I also put up there. So the quiz is due by the Tuesday. All right, so next Tuesday. So you have a week to work on it from when I posted it. Problem set I have due at the end of the week next Friday. So you've got a little more time with that. Once again, it's just going to be related to stuff we talked about prior to today. So just that nonlinear relationship stuff. Okay. I was looking through some of the post-exam kind of questions. So one thing I will start doing, I wouldn't get too reliant on this. But I am kind of having recorded what I'm doing up here now. Because I've switched the in-class quizzes to have a number. I've noticed that there's more people somehow not in class now than there was before I did that. So I'm not as concerned with people trying to kind of class and just rely on the videos. Also, I'm walking around. I know the audio is not great. They're not meant to be a perfect replacement for class. Okay. I also will tomorrow repost that the do file. I'm looking right through it. There it is. This do file, I'll kind of take some things out that were probably a little bit more in depth that we kind of covered than you would need for the problem set. I'll probably also add some comments in just to kind of give some clarification. So I know when I have these do files we use in class, sometimes to go a little bit further, even than what I expect you to do. We've got several examples. If we have extra time, I will sometimes use additional examples. So I'll try to clean those do files up after the end of every kind of section so that when you go to work on that problem set, it's a little bit more, I don't want to say usable, but it's not as much information, some information that you may not need. So I'll keep the old one up there because it does have additional stuff in case you're just interested or want to go back and say, okay, what did we do? I know that's not needed for the problem set, but I was interested in that. I'll put up kind of an additional one and I'll call it like nonlinear fall cleaned up or something like that, right? So it's just a little bit more succinct for you, okay? I haven't went through all of those responses to the post-exam questions with a fine-tooth comb, but those are just a couple things I noticed here and there as I was looking through them. Once again, that was meant for feedback from me to kind of try to make this class more efficient for you, okay? It was also a nice, easy way to kind of get additional 3 points that were added to your exam score. So yeah, total midterm exam score should now be updated yesterday to kind of include those post-exam assessment points. If you did that, I think everyone but like 2 people did that. So good on you guys. Right. I'm looking at current grades in the class just to kind of give you an idea. I think that the mean was like an 80, right around an 80, and the median is like right around an 81 something. So that means we have what type of skewed data? Mean is below the median, so left skewed, right? There's a couple unofficial drops, I think, right now that might be pulling the mean to the left a little bit. But also that grade is currently kind of reflecting if that midterm score was what you get on the final, okay? So we'll kind of mention this, right? Like exam points are probably harder to get than the problem set and quiz points if you're preparing and kind of putting time into those. So I would highly suggest you take the remainder of the problem set and quizzes very seriously. Try to get as many points as possible on those because the final exam will be difficult, right? We're just going through more complex material, so it's only going to get more difficult, okay? So that's kind of a current status of where we're at in the class. Today and then next week, we'll kind of look at nonlinear regression, but in a slightly different context, which is interaction terms, okay? So I call this nonlinear regression. We'll see it's a little bit different, but some of the same stuff that we've used before will kind of apply to these models as well. Okay. Any questions from me before we kind of jump into material here? I'm going to give a little bit of a summary of where we're at. So what we'll start talking about today and continue on through next week is another way we can identify nonlinear relationships. But this includes not just the nonlinear relationship of one variable, but the relationship that can exist between two of our independent variables. Okay. So if I think about kind of this simple setup, right? Maybe I'm trying to predict wages and I have just two simple dummy variables. One identifies if the individual is female, 1 or 0, and then I have one that identifies if they're married, 0. Okay. So once again, these are dummy variables, right? So if we're starting out, what should those coefficients represent? If I don't include any other controls, dummy variable essentially tells me, well, what's the additional effect of belonging to that group, right? So I can kind of think about it as it's the average effect of belonging to that group on whatever my dependent variable weight is. So from something like this, like we use these dummy variables because we can identify things like discrimination, right? Whether it's on a course of gender or kind of choices that you've made in life, you married, unmarried, etc. Right? So you can actually do this and include several control variables here. So I had some salary data, and it's got like all kinds of stuff. So I just threw a bunch of controls in there so that I could say, right, this regression is a little bit more powerful. Holding all else constant, what is the impact on wages of being female and married? Now here, it's a little bit tricky, right? Because it's not an impact on my wages here. I'm using the natural log of wages. So I've got what type of model? A dependent variable, I've taken the natural log. Independent variables, they're just dummy variables, so they're linear. So I have a
log linear.
Log linear. So what's the interpretation become? Well, if I'm going from a 1 unit change, it's a dummy variable, so just going from the 0 to the 1 group, beta 1, or the coefficient associated with that dummy variable, will be the predicted change in my y variable. But if I'm going from a number, not taking the natural log, that's kind of like I'm in terms of probabilities, right? Going to then a natural log, how do I convert to a percentage? I need to take that coefficient and so if I tell you the probability is 0.25, how do you tell me that it's the percentage of 25%? You multiply it by 100. Right? It's not a percentage in our regression to something that is. This is kind of how we said we can remember transformation, what we need to make when we're interpreting these coefficients. So now it would be like the effect of being female, right, relative to not female, predicts that the natural log of wage goes down by 0.38, or that it goes down by, well, I would take that, multiply by 100, so it would go down by 38% here. Pretty large change, right? Holding all else constant. Okay. So what's that really telling me? Women are, say, discriminated against, but essentially, right, they're earning far less than their male counterparts. Holding everything else in this regression constant, their expected wage just from simply being female goes down by 38%. Now, we haven't controlled for like the type of job that the individual has. There's a lot of other omitted variables here. We should probably be a little bit hesitant to start making statements that like we live in this sexist society, but this is at least some initial evidence. So here we can kind of look at both of these groups. That's kind of interesting here. We may not have ahead of time knew this or thought of this, but actually being married predicts that you would expect to see higher wages for the individual. Okay. So this is things we've already talked about. Right. So what we're then going to do is think about, okay, well, maybe, right, a married male is treated differently in the workforce than a married female. Or potentially, right, being female, you might be treated differently if you're married versus not in the workplace. I don't think I'm breaking news to you here. This is likely something that probably exists, right? So these two independent variables that we had, female and married, there's likely some, right, the effect of belonging to those groups might be different, right? The effect of being a female might be different depending on if I'm married or not. And the effect of being married on my wages might vary if I'm female or not. Right? So that marginal effect might depend on this other X variable, or there might be some interaction between these two independent variables. So what I'm going to do is include this third variable, which is just the interaction of those other two. right? I'm just going to multiply them by each other. Now with dummy variables, this gets to be a little bit easier to think about because what would the total effect be if I was, what I have here, married females, right? What would the total effect for a female be if they were married? Well, what would change in this regression if the individual was married and they were a female? This variable goes from 0 to 1, so beta 2 would be part of that effect. But if they're female, what would also get added into my prediction? Now, if they're married, 1 times 1, beta 3 would also get added in. Now, what would the marginal effect be of being married for a male here? Simply beta 2, because if they're male, what does this become? 0 times anything is 0. So that isn't part of our prediction. So we can start to pick up differences, not just between kind of the dummy variable group, but these like different combinations, right, of two separate variables. Okay. So what we're really doing here with dummy variables. So if I had, and I'll just throw out the natural log just for the sake of this example. So if I think about here, I had married. Let me make sure this lines up with the slides. Did I write married first? No, I didn't. We'll start with female so it matches up with the slides. We had married, then we had married times female. So if I think about when I'm calculating a marginal effect, what did we do when we had a squared term? We use it to find turning points. What did I say? The marginal effect is really like I'm taking a derivative. Okay. So what is the change in my wage coming from a change in whether or not the individual is married? Well, here, this is going to vary for the two groups. So if they're female, what would the change in wage be if we looking for marginal effect of being married? Well, for a female, we would have what? Beta 2. And if we take a derivative of this, married goes away, we would have beta 1 times female. So our marginal, sorry, beta 3 times female. I think I said beta 1. So for a female, the total effect, well, this would be a 1. The total effect would be beta 2 plus beta 3. But for a male, the marginal effect would still be beta 2 plus beta 3 times female. But for a male, what's the value of the female variable? 0, so it just simply becomes beta 2. So we can pick up a difference in the marginal effect of being married for females versus males. Now, this is a little bit easier when we have these dummy variables because when I take that derivative, right, for one of those groups, this value would be 1. For the other group, this would be a 0. So remember when we had the marginal effect of a squared model, it was like we had a nice continuous variable. Well, it depends on, the marginal effect depends on that variable. Same thing here. The marginal effect will depend on this female variable. It's just now we don't have to like plot it at a bunch of different points because that variable is a dummy variable. There's only going to be 2 points. Using a little bit of what we talked about before, but it almost seems a little more simple, at least up to this point, hopefully. Any questions on this idea? Okay. So, right, if I rerun this regression, I can do a similar thing that I did when I wanted to include a square term. I can actually create the variable and say like in Stata, and we'll look at some examples here in a second, generate married female is equal to married times female, or I can use this double hashtag method or pound sign, whatever. Well, I guess maybe I'm done. I talked to someone who's 20 years older than me. They're probably going to call that something different, right? But we're going to just kind of use this. We can use it right in regression without creating the additional variable. Now, if it's helpful to create the variable for yourself so that you can kind of think about it, right? And then include female, married, and that interaction term, that's fine. You do it this way, Stata will automatically include the dummy variable of female, the dummy variable of married, and then the interaction of the two. It just gets a little bit trickier if we wanted to like display those coefficients in Stata using that display command. And we'll kind of take a look at that in our do file. But for the sake of what we're doing, we now have the coefficient on female, the coefficient on married, and the coefficient on the interaction of the two, while still controlling for a bunch of other factors. So I now want to think about my different groups, right? So we said that that coefficient on married was simply the marginal effect of being married for the zero group, which female is our dummy variable. The zero group was males. So if you're married and you're a male, the additional increase in wages, we kind of ignore the log just for the sake of making interpretations a little bit easier, goes up by 0.16. Now, what would the total effect or the total marginal effect be for being married for a female? It would be the coefficient on married, but also add in the coefficient on the interaction term. Notice if I add these together, what is my total marginal effect?
Negative.
Positive, negative, about 0.05, right? Somewhere around there. So the marginal effect of being married for males is actually positive on wages, while for females, if they become married, the marginal effect on their wages is actually negative. We can identify if these two different groups, males and females, are being treated differently in terms of their wages based off of this other characteristic of if they're married or not, right? We can allow that effect to vary between the two groups.
So we basically just made a constant like with the zero group, and then we add in the scenario with the one group for that dummy variable.
So you add in a constant for the one group. You can think of it that way, because we're just dealing with dummy variables for right now. I would hesitate to say, think about that only because that constant on married still reflects not just a constant, but it is an actual marginal effect, right? It isn't the constant in the wage for everybody. It's only the constant that gets added in for the one group of, well, here it would be kind of the amount added into the prediction for that one group of married, but for the zero group of what you interacted it with males. So it's a constant, but it's also still telling you the effect of being married just now for the group of males.
So it's really like the bit because it's the zero group is the base for both groups, right? Sort of operates.
It's the base of the marginal effect, right? So when we were thinking about this, that coefficient on married, it wasn't just the constant that gets added in, it's the base of your marginal effect, right? The marginal effect of males was beta 2. The marginal effect for females was beta 2 plus beta 3. So that's where we want to quite think about it as a constant, but in your marginal effect equation, it is the constant. That's why I wouldn't explain it that way, because it's a little bit confusing, but it is going to be in the marginal effect for both groups, right? And then the interaction term coefficient tells you the additional effect or the additional marginal effect for that one group that you interacted your original dummy variable married with. Think about this a little bit different here, just to kind of make the point since you're asking the question. What if I wanted my marginal effect of being female? So here we were looking at the marginal effect of being married. Now we're looking at essentially the derivative of our dependent variable in respect to being female, right? Well, there's two different groups. There's going to be unmarried females and married females, right? So if we think about what's the marginal effect of being female for someone who is married versus unmarried. Once again, if I take a derivative of this function in respect now to female, what does that become? Beta 1 plus beta 3 times married. That's going to be the same, right? If I take that derivative, it's the same for both groups. But for the married group, what is the value of the married variable? 1. For the unmarried group, what's the value of the married variable? So my marginal effect for the unmarried group would simply be beta 1. But for the married group, it would be beta 1 plus beta 3. So here, beta 1 would essentially be kind of the constant component of the marginal effect of being female. And then beta 3, that coefficient on the interaction term, tells us the additional effect of being female if you are also married. Questions? This idea. All right. So here we kind of thought about, this was in the context of the marginal effect of being female. We kind of already talked about if you add in the interaction, we now see that the total effect for a female being married was actually negative, right? So it can vary between the two groups. Okay. So I kind of phrased this question, maybe I've already mentioned it, but let's think about it a little bit harder. So for these two variables, right, the coefficients on just the dummy variables tell you kind of like the starting point for the marginal effect of that group. The interaction term is going to tell us what? The additional effect of belonging to that group if you also belong to this other group, right? It was the additional effect of being female on your wages if you also belong to the group of being married. So you can start to think about this interaction term as the additional effect of belonging, the marginal effect of being female. The interaction term is the additional effect you would see on your wages of being female if you also belong to the group that you interacted female with. This could be married, this could be over 40, this could be whatever dummy variable we're thinking about. So let's go take a little bit of a look here at our do file here. So I think this was the actual data set that I kind of ran those regressions from. So it's just one of those free data sets. We'll kind of open it up. It's called Beauty. These were the regressions I was originally running for you. What I want to do here is we looked at these two right here. Right? So we had this dummy variable example. These were just the regressions that I was showing in the slides. So one thing you could do, you might already be thinking like, this seems kind of redundant with dummy variables because it's actually like something we've already talked about. If I have female and married and the interaction of the two, anytime someone is a unmarried female, the amount that gets added into the predicted wage would simply be coefficient on female. Anytime I have a married male, the coefficient being added to their wage would simply be the married coefficient. The interaction term would be the additional amount added in for a married female. So what would my base group be? When would both those dummy variables be equal to 0? Unmarried male. What does this sound similar to? When we included, go back a ways, like categorical variables, right? And we had to leave one out so that we had a base group to compare to. This is the idea that like if I have a categorical variable like the level of schooling, we had to leave one out, right? Well, essentially we're leaving out one group when we include this interaction term. So what you could do is instead create these variables where married female is just equal to 1 if they're married and female. Married male is equal to 1 if they're married and not female. And then unmarried female will be married is equal to 0, female equal to 1. So if I do this instead of creating the interaction term, what I'll notice is, well, I want to have this to compare it to the old regression so we can have it here. So we had the interaction terms, right? My coefficient on female was negative 0.25, 0.16, and negative 2.11 on the interaction term. So if I kind of use these coefficients, I could actually reproduce those values, right? So if I think about what's the effect going to be for a married female, I have negative 0.29 here, right? That's if I just kind of include just those indicator variables. If I include the interaction term, well, what would be the constant for this kind of married female? It will be 0.166 plus negative 0.211 plus negative 0.25, which would roughly give me what, negative 0.45. So about negative 3, sure enough, or sorry, 0.3, which sure enough, it's about negative 0.3. All right, so interaction terms is really just a different way of including several, like a categorical variable, including those dummy variables. Now, the reason why we might prefer to do this is because those coefficients have a little bit more like application or practical meaning to us, right? To understand like what is the marginal effect of being a married female, it's harder to kind of think about, okay, what two coefficients do I need to find the difference of here to tell me that? Well, I would need to compare it, a married female One married female, that difference was about negative 0.05, which remember, we said, what would the marginal effect be? We did the interaction term. For a married female, it was about negative 0.05. So it's still telling us the same information. We'll still make the same predictions, but it's a way for me to introduce interaction terms with dummy variables before we get to the more difficult continuous variables, right? So the reason why we want to include interaction terms is because we can now identify the differences in the marginal effects of these dummy variables. The next step would be identifying the differences in the marginal effect when I have a dummy variable and I interact it with a continuous variable. There, I can't compare it to something where I've just included categorical dummy variables and left one out, right? Because it's continuous. So, kind of an interesting result. There's kind of two different ways to do the same thing here. I'm just introducing the use of interaction terms because we'll eventually look at interaction terms with continuous variables, okay? So if that's the next thing that we want to do, right? Let's say that I want to predict the marginal effect. And I think here I'm using the beauty variable here that they had, which is like the looks. But I think that maybe an individual's wages might be impacted differently by their looks if they're male versus female. Right? So I think that I've got this continuous variable that represents looks. I've got this dummy variable, which represents are they male or female. And maybe there's some interaction between the two, right? Excuse me. So how might we be able to estimate this, right? If we were using dummy, well, we can't, right? Beauty or looks is like this continuous variable. So we can't just include a dummy, like it's not categorical, right? Excuse me. So what we're going to do instead, because it's continuous, just like we did with the dummy variables, I'll take my dummy variable and I'll interact it with this continuous variable. So what that's going to allow me to do is pick up differences in the marginal effect, beauty or looks, this looks variable, for males versus females, okay? So if I think about my regression that looks something like this, we'll do a very similar thing. We're just now dealing with a continuous variable, right? So try to do it in the same order. And I think I use the natural log of wages here as well. So let's say I have this beauty variable in my data set and it somehow measures looks. Higher values represent higher, better looking people somehow. I think this actual data set, this is a bit of an aside, but I remember they created it by like showing pictures to groups of people and asked them to rank the people on their attractiveness and then stored it all in a data set, which is not creepy at all. But this is how they came up with it, right? So here, I'm now going to include an interaction term of my dummy variable with now a continuous variable. So here, if I think about the marginal effect of beauty or this looks variable, what would it be if I just took a derivative of this function? So if I want to know the change in my wage in respect to beauty here, and we could do natural log of wage as well, it'll be kind of a similar thing, right? But to make it a little bit easier, let's just assume we're looking at wages to make the math easier. If I take a derivative of wage in respect to beauty, what am I left with? This, right, would be beta 1. What would the derivative of this be? Plus beta 3 times female. So what this is really telling me is, oh, the marginal effect of beauty on my wages actually depends on this other variable, which is female or not. So here I would have two groups, and I could say, what would the marginal effect of beauty be for males versus females? Well, for females, this becomes a 1, so I would have beta 1 plus beta 3. Whereas for the males, it's simply going to be beta 1. Now, what this allows me to do, if I'm thinking about a continuous variable, is here I've got my X variable and I've got my Y variable. So the impact of beauty could look something like this for males, right? Let's say, for example, let's just assume better looking people are rewarded in the workplace. There's like a bunch of evidence out there that that might be the case. If I did a line that best fit the data, but I only plotted my male observations, then maybe my line of best fit looks something like this. And that coefficient, right, it goes back to like a simple linear regression. I've got a nice line of best fit that best fits the male data. When I interact a dummy variable with a continuous variable, what it's allowing me to do is essentially, it's like I'm pulling out only the male observations. I'm getting a line of best fit for them. But then maybe for my female observations, maybe they're up here. It also allows me to get a line of best fit, but only for my female observations. So notice here, the way that I've drawn this, well, what was the marginal effect of beauty for females? It was beta 1 plus beta 3. So what did I assume was true about beta 3 here? That it was slope is steeper. I must be adding in a positive or negative value. Positive, right? So I'm assuming that that kind of additional impact on wages of kind of this beauty variable was higher for females than it was for males, right? So I'm essentially picking up differences in the slope between beauty and wage. That variable that I interacted, this dummy variable, that continuous variable I interacted my dummy variable with. So the reverse gets a little bit trickier, and I won't kind of push us that far, especially today. If I think about the marginal effect of male versus female, and then there'd be tons of different beauty variables we'd have to make the marginal prediction for. For us, we're just thinking about when we interact a dummy variable with a continuous variable, it allows us to essentially pick up that the effect of this X variable that was continuous might vary between these two groups. Okay? So picking up differences essentially in our slope for that line of best fit. Okay? Questions on this idea before? Okay. All right. So with that idea in mind, right? Got the regression results here, but might as well just do some additional work in this data since I've got things kind of set up similar way. So we'll go back here, and this is where I'll add in some stuff here. Okay. So let's look at this example where I'm now interacting a dummy variable, whether or not they're female, with this beauty or this looks variable. So I can do that, right? If I just run this regression on its own, I don't include an interaction term. Okay? So if I do that, looks like, okay, as someone is deemed more attractive by their peers, their wages are increasing. If they're female, we would predict, holding everything else constant, their wages are actually quite a bit lower. Now, if I think that there's some interaction between those two terms, if I include an interaction term, start to think about some other things that are going to change. So I can use this way where I don't have to create a new variable. Let's just say I don't like that, and I like to kind of keep things, I like to name things, and it just keep it a little bit more obvious to me what these variables are. I'm going to create this variable and call it female looks, which is just the female variable times that looks variable. So I'm going to go ahead and create this variable. Right, that's my interaction term. I'm then going to run that same regression, but instead I'm going to include the interaction term that I've created. Okay. So why might I want to do this? Well, if I want to start to like use the display command, now I know that I can use the coefficient on this interaction term. Whereas if I use the kind of double hashtag, remember what we did with the squared model? It started to become like I had to call it whatever the continuous variable was, but only one pound sign or hashtag. It just gets a little bit more confusing. So if I run this regression, hopefully it gives me the exact same results as if I didn't create the variable. So we can just prove that to ourselves real quick. So it looks like 0.039, negative 0.53, 0.04. Negative or 0.039, negative 0.53. Okay, it does the exact same thing. I'm not lying to you, right? So if I've included kind of the interaction term, what this is telling me is what is the marginal effect of looks for a male? That as their looks goes up by 1 unit, how much is the predicted wage changing by? Just 0.039. Now we can scale this up. We're using the natural log of wage. So, we could kind of convert this to percentages, but just for the sake of not throwing in multiple concepts, we just care about the directional change here, right? That slope is going to be 0.039. What's the marginal effect of looks for a female? Well, it would be that same 0.039, but what would also get added in? The coefficient on the interaction term. So now the marginal effect of looks would be twice as large, more than twice as large, right? It's like 0.086. So you have almost twice as steep of a line for females and males, or essentially the marginal effect of a 1 unit change in this looks variable is twice as large for females than it is for males. We can identify kind of differences in this marginal effect for this group of this continuous variable that we had, which was looks. Questions on that idea? Now let's try to relate this more big picture with other things we've talked about. When I include the interaction term, what should definitely happen to my R squared? Well, it's essentially like I've included another variable, so my R squared has to go up. So if we compare this to the one where we didn't include the interaction, our R squared goes what? 0.4071 to 0.4077. So it went up a little bit. We don't know how much it's going to go up by, but we always know it's going to go up. Now, does my adjusted R squared have to go up? Not necessarily, right? Our adjusted R squared, we go all the way back to when we were looking at that equation prior to the last exam. It penalizes us for including more variables. So 0.4016 went to 0.4016. So here, one of them is going to be higher or lower. We can't see it out to the fourth decimal, but one of them is definitely going to be larger, right? Or smaller. So we don't know what direction that adjusted R squared will change. Here's a nice example where you can kind of show this, like it could actually technically stay exactly the same. Now, if my adjusted R squared doesn't go up when I include the interaction term, what did that mean? That I'm adding in that interaction term that I couldn't really explain any more of the variation once I kind of adjusted for that I was including another variable. So if I can't explain much more of the variation in wages, my dependent variable, what's probably true about the statistical significance of that interaction term? It's likely not statistically significant. If my adjusted R squared went up, what would probably be true about the statistical significance of the interaction term? I'd be more likely to find. Now, obviously, it's going to depend because when we talk about statistical significance, we just have 3 benchmarks. And just because it doesn't quite meet our benchmark, like let's say we had a p-value of 0.11, okay, well, that's not statistically significant, but it's really close. So you could still see your adjusted R squared go up and it just barely misses that mark. But we at least know that in this example, if the adjusted R squared stays about the same, we probably should be pretty far from those benchmark levels of statistical significance. Sure enough, if I look at that interaction term, and I'll use the one where I created the variable, we're pretty far away, right? We're at 0.24. We're not really close to 0.1 at all. Okay, so a lack of statistical significance on the interaction term and a lower adjusted R squared would suggest that the interaction term should or should not be included. Shouldn't. We're not gaining any additional information from that. So there's likely not an interaction between these two variables. So even though I found that the size of the effect was considerably higher, I can't actually say at any statistically significant level that males and females are treated any differently in terms of their wages for this looks variable, right? Because it just wasn't statistically significant. So this is where we have to be careful. When we look at coefficients, yes, when you include an interaction term, you will find a difference in the marginal effect. But can I actually say it's different? Not at any of my statistically significant levels, right? That p-value of 0.24 is quite a bit above all my benchmarks of 0.01, 0.05, and 0.1. Okay. Is that any questions on that idea? Okay. Now I'll kind of show you what we could do. And if we create the variable, it might make it a little bit easier. So let's say I wanted the marginal effect of looks for males. Well, if looks goes up by 1 unit, for males, what's going to change in this equation? Only the looks variable. So the only change in wages, if looks goes up by 1 for males, is going to be coefficient on that looks variable. Now, what if I wanted the marginal effect of looks for females? I can type. Well, it's going to be that coefficient on that looks variable, but also plus the coefficient on the interaction term. Now, I could do that from this regression where I didn't create my own variable, but now I have to remember that this is actually what C dot looks, 1 pound sign in female, and it just gets a little bit kind of harder to deal with. That's why I always say, like, when we're running these nonlinear models, yes, you can do it without actually creating the variables, but when it comes to like actually using those coefficients in Stata, it's probably a little bit easier to create them yourself. Now, this kind of goes out the window if we kind of got to the next level of a stats or like applied stats, or if we're dealing with like 500,000 observations, well, then creating new variables in our data set starts to like run into like storage space issues. We're not, we're not dealing with anything like that. So for us, it's probably just more practical to create those variables for ourselves as opposed to using kind of that shorthand that's like built into Stata. Does that make sense what I'm saying there? And this is where sometimes if I don't include things in the do file, maybe I'm adding things in class, you could always have the do file pulled up during class and kind of replicate what I'm doing, right? I'll save this here so that I have it and kind of when I'm posting these more cleaned up versions, we'll also have what we did in class here. Okay. All right. So what I want to do here. Got what? We got 30 minutes left. We talked about differences in slopes. We talked about the R squared. Got a second example down here, don't I? So I kind of already went through this, so I'll kind of quickly go through the slides just to kind of connect what we were doing. So we ran the regression without the interaction term, right? We then ran it with, and we saw there was kind of an additional effect for females of looks, right? Talked about the adjusted R squared and the R squared, right? So R squared has to be greater. We don't know about the adjusted R squared, but if the adjusted R squared goes up, it's more likely that interaction term will be statistically significant. If it goes down, it's less likely. And then we kind of looked at how do I calculate those marginal effects? It's really just going through and taking the derivative. Now, if I think about, add those lines of best fit, I told you something about the slopes, but when I drew these out, I also had possibly different starting points. So where do those starting points come from? So if I think about, for an individual in this example, try to use colors here, 0 as their beauty, right? For males, where would their wages start out at? Well, if we assume that we don't have any other, by holding all the other variables constant, we would have that intercept coefficient. Then for males, that's all we have. Because female will be 0, 0. So when beauty is 0, that kind of line of best fit just starts out at our constant, right? For whatever that 0 group is. Where would the line of best fit for females start out? They would also have kind of beta 0. Now here, if beauty is equal to 0, these kind of go away. What are we left with if we're now looking at the female group? Beta 2. So including the interaction term doesn't just allow us to identify differences in the marginal effect or the slope, but it also allows us to identify the differences in the starting point for those groups. So it's a little bit kind of trickier to think about there. What we probably would focus a little more on is that difference in the marginal effect. But when I drew this, just to kind of make sure, like, it isn't always going to be starting at the same point. In fact, when you include the interaction term inherently, you're allowing that. I think we talked about this with what dummy variables do. With just a dummy variable, it allowed us to pick up like 2 different groups, but they were like parallel shifts. When we include the interaction term, we still allow for that line of best fit to shift, but we also allow for it to change its slope for that group. We're kind of allowing for like more variation than we were before. We include these interaction terms. Any questions on this side? Yeah.
So this is just, it's different from the way you wrote it, but Are we using the same wage data as we did before with that start out negative? Because the female wage data is naturally.
Yeah, I don't remember what the values are, right? Yeah, if I had negative, if these are negative, right, then I just have to move my x, like where this x axis is.
So that means the difference is really just the natural wage gap between genders.
The natural wage gap between genders, right? It's a little bit different, right? Because what does beta 2 represent? It's the difference between the two genders if, very specifically, this continuous variable is equal to 0, right? In fact, if the way you're phrasing it, a little outside the scope of this class, but you're asking the question. So the actual average difference in the genders from this looks variable would be like the average of the difference between these two lines across every value of looks. I mean, it gets harder to think about, right? Like I would actually have to be looking at every single value for looks. I'd look at what the difference is between those two groups and then take the average of that. And that would tell me the average difference between. So it's a little bit different. This is really just kind of telling me that the starting point, right, for these two groups is different, right? And it's just in kind of relationship to kind of this beauty variable, right? But then as beauty changes, that gap or that difference between the genders, in this case, the way I have it drawn is increasing. And the way they line up the data, because that coefficient on the interaction term was positive. Now you could technically, like, let's assume we had an example just to kind of make this point. Let's assume, oh, I don't know if I want to put it this far yet because I don't want to confuse anyone. We'll wait till we get to our second example, and then I think I have something that I'll kind of touch back on your question, okay? But for right now, we're just thinking about that, we're really focusing on that coefficient of the interaction term allows us to pick up a difference in that slope.
So just to clarify, for like a quiz question or an exam question, how do we interpret the gap between any of these situations, like the gap between these two variables?
What do you mean the gap between these two?
So there's a difference in starting point, and there's a difference in wage, right? Is just the wage difference between every single observation?
No, so I mean, I wouldn't ask you about that, but you could technically tell me what the difference is in the predicted wage for males and females for every single value of this beauty variable. I'm likely not going to ask you a question like that. What I'll ask you about is what is the difference in the marginal effect? Well, the difference in the marginal effect would simply be that coefficient on the interaction term. Yep. Or from our regression output, right? That difference simply be 0.04. All right. Any other questions? We keep moving here. Skip this because we kind of already looked at these results. So just to kind of round out this discussion, because I think it's interesting. Get all this on this. There we go. I put some links up here, and this is applied stats course, so like I'm not going to ask you like go read these papers, but if you are interested, they did a similar thing. So this is like an old data set, but they actually went out and looked at this was specific to economics. It's a website called Joe, and it's where all economic jobs are. Like if you have an econ major, you should be looking on there for postings of jobs. And what they found was they did a similar thing, but they used LinkedIn profiles. So they used the pictures on someone's LinkedIn profile and had like a random group like rank them so that they then had like a continuous measure of what the looks were for all these applicants. So instead of wages, they were looking at the number of interview requests that the person got. And they did a similar thing. They took this like beauty ranking of the LinkedIn profiles, they interacted it with female. And what they found was beta 2, right? So that's just whether or not you're female, right? That was kind of the difference in our starting point. So it's like assuming if you had two people who had looks ratings of 0, would a male or a female, if that value is positive, that would mean females get more interview requests given that they both have looks ratings of 0. So they kind of start out at a higher point. But the interesting thing that they found was that this beta 3, that interaction, all right, was also kind of similar to our example, positive. So that meant as the looks rating or that looks variable went up, right, what actually happened to the number of interview requests that two people with the same amount of looks, right, same looks rating, but one of them was female, the female got significantly higher interview requests, right? That marginal effect of that looks variable was steeper for females, right? So I don't know, I thought it was kind of some interesting papers where they actually like were academic papers that looked at this. There was one that did something similar. I think Jon Stewart like summarized it. So it's like an older show now. You guys know what the Jon Stewart show? Some of you, okay. It's kind of a funny, look, it's meant to be comedy. And if you watch this, nothing on what I think or anything. I'm not lining up with exactly what he's saying here, but it's kind of a funny little take on this paper, which essentially was showing that there's differences in these interview requests or wages based off of females and males. Right? So that's just kind of a real world example we can look to of why we want to include these interaction terms. Okay. And here was kind of one of the tables from the paper. So what actually was interesting is they found that technically here, the coefficient for just being female, when the looks rating was 0, it actually wasn't positive. It was actually negative. Right. So at the low end of looks, females actually got fewer interview requests. But then as that looks variable went up, at a certain point, females started to get more interview requests. Right? I won't quite push you as far to do like turning points with the interaction quite yet, but we could start to think about like where that would switch, similar to what we did with our nonlinear kind of square term. Okay. And we looked at this already. We'll come back to the turning point, I think, next class. I had another example that we can kind of use to get at this. So I'm going to skip through this example just for today. I want basketball shot data. Well, let's see. Hopefully I put it in the right file. NBA shots. Nope, because I didn't run my global path. Now, this should be one of the files that I gave you on Canvas. It's called NBA shots. So we've got this opened up. I've got 130,000 observations here. I'm going to create this dummy variable. We might have two here. We could use either one. So one was just the position in basketball that they played. Were they labeled as a center, a forward, forward center, a center? All right. So it's just telling us that they're a tall person, right? And then I had their height in inches. So I'm creating another dummy variable that is identifying if they're tall just by are they taller than what? This would be, 7'8". 60 inches is 5 feet. So 72, 6 feet. Yeah, so 6'8". So they're pretty tall, right? So we're gonna create these two dummy variables. I'm now gonna just kind of regress, right? Whether or not the shot was made on if they're tall. Right? If you're not familiar with basketball, you don't really need to be. But generally, people who are taller just aren't as good as shooters. Now, there's freak athletes that's not always true for, but in general, right? I'm playing basketball because I'm tall, not because I'm a good shooter necessarily. Right? So if you just run this very naive regression, it actually looks like the probability that you make the shot because you're tall actually is what? It's significant that it's positive. So maybe being tall helps you make shots more likely, but we've omitted a lot of important factors, right? So I went through and I found like all these kind of interesting data points, like the mean of the player, like across the season, what the attendance of the game was, how much time was remaining in the game, the angle that the shot was taken at, the defender distance, all these control variables. And what I'm now going to do is take this tall variable and I'm going to interact it with how far away the shot was from the basket. So in almost any sport, if you don't like basketball, the further you are away from something, is it going to be harder or easier to kind of have that be successful? More difficult, right? But for someone who's taller, maybe being further away, it's even more difficult for them, right? So we think there might be an interaction between these. So I included this dummy variable, was the person identified as tall or not? And then interacted it with this continuous variable, which was shot distance, which I believe was feet from the hoop or something like that. Right? So if I run this regression, right, how can I kind of think about these coefficients? So maybe we'll build out similar to what we were looking at before, something that looks like this, right? So I've now got whether or not they were tall, identified as being a tall player, I got the distance they were from the basket. So I also have the interaction of the two. Okay? So if I'm thinking about plotting these points, we were doing was saying, okay, was the shot made? That was our dependent variable. We had this dummy variable of whether or not they were tall. We had shot distance. And then we had the interaction of the two. So if I'm interested in plotting out this point, just to kind of give this a nice visualization, if I'm interested in the relationship between the distance of the shot and whether or not the shot was made. Okay. If I'm thinking about for individuals who are not tall. Okay. So for individuals who are not tall, when the shot was taken from 0 feet, technically, where would this start out? So just to kind of have these values so we don't have to talk about them just in terms of coefficients. This was, this is what? Negative 0.05. This was 0.004. And I'm just rounding so we can just kind of have a little bit easier values to deal with here. Okay. So this was the regression output that we just had from this data. I'm just grabbing what those coefficients were. So when the shot distance is 0, what is kind of the predicted, well, if I have a dependent variable that's 1, 0, it's the predicted what? Dummy variable is the dependent variable. The units would be, review of what we've already talked about. Close, not percentages. If it's a dummy variable going from 0 to 1, 0 would mean 0%, 1 would mean 100. So changes would actually be changes in the probability the shot was made. So if I think about someone taking a shot 0 feet from the basket, right? If they're not tall, where would this start out at? Beta 0, which I think the constant here was like, got that one, 0.179. Okay, so 0.179. Now, what's the marginal effect of shot distance? So if we think about the marginal effect of shot distance here, it's the change in the probability that shot was made coming from a change in that distance. So if I take a derivative of this function in respect to shot distance, what am I left with? Beta 2 plus beta 3 times, were they identified as a tall player? Right? So I will have a different marginal effect with different groups here. Okay? So for the non-tall players, what would the marginal effect be? Simply the coefficient on shot distance, that continuous variable. So here I've got what? My line of best fit would have a slope of 0.004 or just that coefficient on my continuous variable. Now for the second group that was identified as tall, where would their predicted probability that a shot being made start out at if shot distance was 0? Beta 0, but also plus beta 1. Well, beta 1's negative. So where do they actually start out? 0.179 minus 0.05, or about 0.129. Right? So they're going to start out initially very close to the basket. Excuse me, the probability they made the shot actually is a little bit kind of lower here, right? Which might be kind of counterintuitive, right? We might not have thought about that initially. Individuals who are tall are actually less likely when they're close to the basket to make the shot relative to someone who's not. Now, we might have some limited variable issues, things like that. Maybe we don't have the right controls, but at least in terms from this regression output. Now, what is the marginal effect of someone who's tall? It'll be beta 2 plus beta 3, or, sorry, I wrote beta 2 in here. Yeah, beta 2 plus beta 3. 0.004, and this was plus 0.002. It's kind of weird. Once again, maybe it's a counterintuitive result, but the slope here actually ends up being a little bit higher for those tall players. As they're further from the basket, oh, hold on. I'm doing this completely wrong because I forgot something. Nobody called me out. What? Where do I have here? This was, this is negative. That's going to change things quite a bit for us. All right. So we'll draw the visual out so it actually lines up with the numbers now. Sorry. So no change when we were just thinking about these points. And so here, this was just going to be, oh, sorry, talking and I'm drawing. Shot distance, whether or not the shot was made. So it starts out at 0.179, but the marginal effect for the non-tall group is just negative 0.004. So I actually have a line that looks like this, right? So because that was negative 0.004, I have a downward sloping line for the kind of non-tall players. Okay. Now for the tall players, this point still the same. We had the right values there. So it's going to start out lower. So this is at what? 0.129. But what's the marginal effect for them? It's 0.004, negative 0.004 plus 0.002. So the decrease there is actually going to be a little bit right? Negative 0.004 plus 0.002 would be about negative 0.002, right? So for our tall players, the marginal effect of shot distance is actually a little bit smaller. Right? It's a flatter curve, which we might not have thought about initially. But I also was kind of irresponsible. I don't actually know if these lines ever cross. I'd actually have to do some math to figure that out, right? This starts out so significantly lower that potentially I could have something that looks like this, where they're converging, but they never hit, right? You know, because the basketball court is only so far, right? We'd have to do a lot more back of the envelope kind of calculations to figure out if they ever do converge. But here we're just thinking about we could plot kind of the directional changes of that marginal effect. Sorry, I forgot the negative sign there and wasn't thinking about what I was doing. Okay. But the end result is still I can identify differences in this marginal effect for my different groups. Okay. So we'll talk about finding maybe those turning points where those two kind of marginal effects would converge next class. Before we leave today, I have some additional examples that we can kind of work through. And take a look at them here. Okay. So got this in-class quiz. I believe the number is 10.09. So 10.09 get us into that quiz. We don't want to spoil the answers here, so we'll kind of take a look at this. So I had this data set that had kind of mate height. So this is like couples and what the person's height was versus what their mate's height was. So if I'm looking here, so I have trying to predict somebody's like, you know, spouse's height or girlfriend or boyfriend's height, given their own height, and given whether or not they're male, and an interaction of the two. Okay. So based on this output, if I was plotting the predicted mate height for different levels of an individual's own height, and I want to do it for males relative to females, which of the following would not be true? Okay. So when we talked about the coefficient on male, what is that going to do? When we were drawing out those visuals, that was going to shift where my line of best fit. What? So the coefficient on the dummy variable just changed where the line of best fit started when our continuous variable of height now is at 0. So if we're thinking about 10.99, that's telling us that the intercept of mate height for males is actually going to be a little bit higher. Okay? So this one should be true, right? That when we were looking at this continuous variable of height, when it was 0, right, we have two groups, males and non-males, males and females, right? So that male coefficient will tell us where that line of best fit for that group starts out. It's going to be 10.99 higher, so that intercept of mate height, our dependent variable, is going to be 10.99 higher for males. That one's true. Now we think about for males, the slope of their own height or the marginal effect. What tells us about what the marginal effect of height would be for males? Well, it would be what coefficient? So if we're thinking about their own height is changing, hopefully one of those coefficients we can easily identify that we should be using would be what?
The male height. Male.
Well, no matter if I'm looking at males or females, what is going to be part of the marginal effect of your own height here on mate height?
Right.
Beta 1. Yeah, the coefficient on height. So we know we'll have beta 1. So we've got what? 0.67. But for a male, right? What is going to get added into that marginal effect, or what essentially would be the slope of that line of best fit? It would be 0.67, but for males, we would also add in the interaction of height male. So 0.67 minus 0.27, the slope for males that on that marginal effect is actually going to be flatter, right? Because the interaction term now has a negative value. So the slope, right, or the effect of bone height, that marginal effect, is going to be flatter for males because our interaction term had a negative coefficient. So for females, right, will the slope be flat? Well, first of all, if you're doing a multiple choice question, one of these has to be true and one of them has to not be true, right? Males can't have a flatter slope, females can't, right? One of those is going to be true. So what would the slope or the marginal effect of height be for females? It would simply be 0.67. So is that slope for females going to be greater than or less than males? Well, 0.67 is going to be greater than what? About 0.4. So this one is going to be the one that has to be true. That slope for females is actually going to be steeper, right? Because when we're calculating the marginal effect for females, we don't add in the interaction term here because the interaction term or the marginal effect of height, that interaction was for our male group. Right? We interacted with that dummy variable of male. So hopefully this last one is going to be true, which is that for females, the intercept of mate height is going to be lower. Well, kind of same thing. This is really just a different way of saying the one we already talked about, right? If male's intercept is going to start out higher, female intercept had to start out lower. So sometimes drawing these out and thinking about these visualizations of what we're looking at can help. But really here we're focusing on that marginal effect. That interaction term is what tells us the difference in that marginal effect. If the coefficient on the interaction term is positive, it means the one group for that dummy variable has a steeper slope. If that interaction term if the coefficient on the interaction term is negative, that tells us that the one group for that dummy variable actually has a flatter slope. In this example. So any questions on that idea? So the only one that was not true was we said what? Females have a flatter curve here. They're actually going to be steeper. Two other questions here. I don't have a whole lot of time. So let's say, what's this one? We'll talk about turning points next class, so don't worry about question 2. So we've got question 1 answered, hopefully. Question 2 we actually could answer, although we haven't really quite went into it, but using what we've talked about before and what we've talked about today, I'll kind of end class thinking about this idea. So if I've got the same regression results, right, but I'm thinking about I want to predict mate height, and I want to do that for someone who's 69 inches tall, right? What would be, how would I go about doing that, right? So if I just want to predict mate height for a male who is 69 inches tall, what would I do? Well, are they male? Yes. So I would put a 1 in here and a 1 in here. So what gets added into my prediction? Beta 0 plus beta 2, right? That gets added into my prediction for sure. If they're 69 inches tall, well, then my height variable becomes 69, right? So I would take the coefficient on height. It doesn't simply get added into my prediction. This is going back to like stuff we did prior to the last exam. I would take that coefficient and multiply it by the value of that variable, right? So whatever beta 2 is here on height, 0.67, I would multiply that by 69. Now the interaction term is where we've kind of already done this. We just haven't used it with interaction terms. What will get added into my prediction from the interaction term? Well, beta 3, for a male, that would be 1. Height would be 69. So all I would do is take beta 3, multiply that by 69 times 1. So it's just like we were making predictions before. We're taking these hypothetical values for our x variables. Here it was just 1 and 69. And that's just a matter of kind of plugging those values in to come up with our prediction. So it looks just like what we were doing before. It's just that I don't just have a coefficient times a variable. I have a coefficient times that variable times another variable, right? So if I was doing this here, someone can help me out with a calculator unless I can get open here pretty quick. What would we actually be doing here? So to come up with my prediction, I would have my constant. Right? I would then add in the coefficient on height, which was roughly 0.67, multiplied by how tall was that person. I would then add into that, were they male? Yes. So I would take the coefficient on male. That gets multiplied by essentially 1. Right? Now for the interaction term, if I round this, go to the full decimal here, I would take the coefficient on the interaction term, but it gets multiplied by the height. But also, if the individual is male, I would then need to multiply this by 1. So if I do that, I get what? About 65.6 inches. All right, so I think I have this set to be a margin of error. So as long as you're close, it should kind of count this as correct. Now, if I'm making this prediction, let me use Excel here. Maybe I won't be doing this. All right. Well, you can't quite, it's a little bit small, but if I'm thinking about, let's say I wanted to make the same prediction for a female who is 69 inches tall. What would I change in this equation?
Change the 1 to the 0.
Yeah, the 1 would be a 0, which I could save myself some time because anything times 0 is
0.
So that wouldn't get added in. But also notice if this is 0, that coefficient on my interaction term would also not get added in. So we're really doing the same thing we were before when we're making predictions. It's just that we now have these interaction variables which are a little bit different. And then next week, we'll talk about, okay, this might seem like really stupid, like, okay, that's pretty obvious. But what happens if I had a continuous variable and I interacted it with another continuous variable, right? Then our predictions, we're not just going to have 69 times 1, we would have 69 times some other value for that x variable, right? So we got to walk before we can run. So is anything, other questions? We're having a discussion over there. What's going on?
The answers.
Oh, all right. So what did we say the answer is? 65.
1.6, I didn't know if it was for 2 or 3.
We're just looking at 3 here.
Okay.
Yeah, we skipped 2 and we said we'll kind of get to that next week. Okay. Any other questions before we kind of end things out here today? See people scrambling. I said, I know it's small, so 65.6. You're not looking at me and you're worried about looking at the screen. I just said it's 65.6, okay? So we're kind of starting out with some more simplistic examples using some dummy variables. It'll become more complicated next week. We'll start to look at interactions between continuous variables.
We got the first one wrong.
I might just have it. I just pulled these questions, so I knew that we wouldn't have time to get through all of them. I'll make sure after class I kind of get these updated, but it should be right. Looking for which one's not true. That was going to be that the female slope was flatter, right? Female slope should actually be deeper. As long as you kind of go with this one being not true, I'm going to sit afterwards. Okay. All right. We'll pick up in this stuff next class. Start early on that problem set because we're just going to get further and further removed from that material, even though it's not due until the end of next week. All right. Take it.